There's one more thing we want to talk about with the non-dispersive wave equation, which is the D'Alembert solution to the wave equation. So last time we found that there was this plane wave formulation, and it solves that for sure, and then we have all these coefficients we have to find, and that can be pretty complicated. There's actually a significantly easier way to find the solutions if you know what the initial conditions are. So like I said, all the initial conditions give you all these coefficients, but the once you get the crests and the troughs and the waves themselves, they don't transform as they propagate along. The crests and the troughs all propagate at the same speed. They're non-dispersive. So let's see if there's a way we can write a solution kind of by a guess and check method that does even better. It makes it easier to set to the initial conditions. So in this, we have kx plus ly plus sigma t, or minus sigma t. So you can actually think of that as k, the wave number vector, dotted into x, the distance vector, the position vector, minus sigma t, or plus sigma t in the two cases. Alternatively, I could divide through by the magnitude of k, and think about this as a vector relationship, where I am looking at position minus some velocity, wave velocity, not wave speed, times time. And that velocity in this case is just going to be the speed times, this is, we know this is, we already talked about how this is propagating in the direction of the wave number. So if I just take the direction of the wave number over the magnitude of the wave number and multiply by c, and then call that c my c vector, then I get something like this, where x the vector minus c the vector t is really similar to this divided through by the magnitude of k. All right. I also could have done it the other one. I could have had an x the vector plus c t. And let's think about what these mean. Well, this says, as if I were to increase an x, how could I keep this number constant? Well, if I increase x in the same direction as the velocity, as time increases, this would be unchanging in time. Similarly, if I go backwards, so now x in the direction of negative c t, this would be an unchanging parameter in time. And now here's the really surprising thing. Let's just consider any old function of these two parameters. Phi of x minus c t plus, and let's call that the minus one, plus phi plus of x plus ct. Okay. I haven't done anything fancy here except for this little bit of work. And it's similar to these equations that these also are functions of this, which is closely related to this, just divided through by k. But what happens if I just plug these general formulas into our original equation set? Let's see. Okay. Time derivative. I take the time derivative of this. Well, I can't take the time derivative easily because this isn't an obvious function of time. It's an unknown function of time. But I can take the derivative of this with respect to its argument times the derivative of what's inside. We can use the chain rule. And so I can take the second time derivative of this, which is just the second derivative of this function phi minus with respect to its argument. And each time I take the time derivative, I'm going to get a factor of c out, minus c out. So I get 1 minus c, and then I get a second minus c. I'm getting those from taking the derivative of what's inside with respect to time. And actually, I should have said it. I get a c the vector each time. But if I do that twice, it actually dots together. And I get c squared, the magnitude of x minus ct. Do the same thing on this side. I get, do it twice, plus c squared phi plus, second derivative with respect to its argument, x plus ct. Okay, cool. Well, let's look at the other side of the equation. That was the time derivative side of the equation. What about the other side of the equation? Well, it says I should go in here and I should take a second derivative with respect to space of that same function and multiply it by c squared. So what does that look like? Well, I take the c squared, multiply it by out in front, and the question is this equal to what I'm going to write on the other side? So when I take a spatial derivative with respect to phi minus, I get phi, second derivative with respect to its argument, once for the first derivative that's in div, second derivative that's in div, and x, the vector, this is where things get a little shaky. When I do that, I get the same old thing back because there's no coefficient on x, the vector. C squared, phi double prime, plus, get the same one for this one, x plus ct. Wow, look at that. Any function of this form with a thing that is propagating in the positive c direction and a thing that is propagating in the negative c direction is a solution to this equation, because here's the time derivative part gets the c squared from the time derivatives, and the spatial derivative part doesn't get any c squareds, but it's got one up front in the governing equation. So this D'Alembert solution actually works as well. We've chosen one particular C orientation that we're propagating those waves in. You actually could superimpose these with a variety of different C orientations, and all of those would be solutions too, because this del squared here and this C squared here are independent of the direction that you're looking in. Thanks.